In this video, we're going to first determine the no-load speed of the motor, and then the stall torque of the motor. And then for three different speed ratios, we're going to test the robot on inclines of 0 degrees, 8 degrees, and 16 degrees. And we'll just time the robot over a distance of 60 inches to determine its velocity, then compare that velocity to the velocities we calculated through our analysis work.
Okay, so what we're going to try and determine right now, we have the motor, there's nothing connected to it. We want to determine the no-load speed. So I have my phone here, and so we're going to do a test when we'll just count the revolutions over 30 seconds, and then we'll be able to figure out what the speed is. So, alright, I'll get this on the top, and we're ready. 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. We just determined that we counted 49 revolutions in 30 seconds, so that means that the no-load speed is 98 RPMs, or 98 revolutions per second. So now we want to determine the stall torque. So to do that, we're going to use this wheel, which is a 4-inch diameter wheel, so it has a 2-inch radius. So you can use these zip ties that came with the kit, and then I'll apply a second one so that we'll be able to use a spring scale here. Okay, so we'll pull it like this, and we'll put this on here. And then this is just a direct drive off the motor here. Okay, so I'm just going to take this collar off here so we have room to get that on good. Okay, and I'll just put this back on to make sure this doesn't come off. All right, and you want to have somebody I have this mounted on this box, but I want to make sure it doesn't fall off when I do this. Now, the key here, so we want to get this so that it's pulling tangent, right, not pulling like this or some other way. We want to make sure that the moment arm is 2 inches, so it has to be perpendicular like that. Okay. Now, when we do this, you want to do it very quickly because these motors overheat very quickly if they're stalled, and that's not good. So we'll just do. Let's see. We'll do a quick test here. Right. Ready. So get this set up. I've got to turn this on, it would help. Ready to go. Just waiting for the joystick to connect with the Cortex. And that light turns green. There we go. All right, so we're ready. We'll just go quickly here. Okay, and I'm going to give that another try. Looked like we had about 14 newtons on the scale here. So we'll try that again. 14 newtons. So now we'll be able to convert that into pounds and multiply by 2 inches to calculate the stall torque.
Okay, so we determined that the force there was 14 newtons. And 14 newtons equals 3.15 pounds force. Okay, so we have our wheel, and we had this force, and we know that this radius right here is 2 inches. All right, so our stall torque then is just going to be equal to that force, which is 3.15 pounds force times 2 inches. And so that turns out to be 6.3 inch-pounds force.
Okay. All right, so we're going to run tests on this ramp, and we want to do 3 different ratios. So we'll start out in the low ratio, and so in order to do that, we're going to, let's see, put a small gear on the motor. All right, this is a 36 tooth, and then we'll put the 84 tooth. So now we shipped you some of these. Some of them it's kind of tight, so you probably need a pair of vice grips or something to push this on. And after a while, you can get it to loosen up a little bit. So, and you want to put in the spacers so that the faces line up properly. So, let me see if I can get this on. All right, so in other words, I have spacers adjusted here so that the gears line up. In other words, you don't want them so that the 2 gears are kind of offset. You only have partial engagement, right? We want them. These faces should be flush like that, okay? And so now we can put the collar on this one. All right, and then we'll put a spacer put another spacer here, and then put this wheel on the back. And you can see that, again, that this is a 36, and this is an 84. So this gear, the motor is going to has to turn more than, or faster than the big one. But you have the motor, the torque that will be delivered to this shaft will be greater than the torque required from the motor. And the way to think about that is Newton's third law: for every action there's an equal and opposite reaction, right? So the force on the teeth is the same, but the moment arm for this small gear is shorter than the moment arm for the bigger gear. That means that the torque on this shaft is going to be less than the torque on this shaft. The force is the same, but the moment arm here is bigger than the moment arm in this one. So therefore the torque on this shaft, it will be spinning more slowly, but it will be spinning with more torque. Okay, and then I have lots of spacers on this front wheel, so that the wheel we don't want the wheel to rub on the gear here. So I have plenty of spacers there. You know, you don't have to you just want to have a little bit of clearance there, right here. You don't want that edge of the wheel hitting the gear. Okay, so now we'll put this collar on. Okay, and you'll also notice that I have these 2 bricks. So you want to get some weight, and what I've done to keep the arm stationary from back driving is I just took the larger diameter Allen wrench and put that through the holes on the gear all the way to the other side, so that now that keeps the arm from coming down. So the way I have it set up, the arm itself is pretty much horizontal. Okay, it's pretty much horizontal, and it won't go down. But I had to add some weight because the motor produces too much torque. In other words, we want to be able to get to a test where the low range goes faster than the middle or the high range. And the problem is, because the robot isn't that heavy for these motors, you end up just losing traction. You have to go to such a high angle of the ramp that you lose traction before you actually start to approach any kind of stalling on the motor. So the way to require more torque for a given angle, in other words, without changing the angle of the ramp, if I add weight, that adds weight down here on the wheels, and then before the wheel slips, the coefficient of friction hasn't changed, but there's a greater normal force. So now it's going to take more torque. We have more weight we have to get up the ramp. So that's just a way so that we can try and get to the points on the power curve that we want to demonstrate. The other thing I can point out here is if you add some weight, make sure that the angle that the robot tips is not smaller than the angle of the ramp. In other words, you don't want to try and run this test and have the robot tip over. So on my phone, I have an app, and you should be able to get this app as well. It's called Angle Meter. Okay, and right, so you know, if I can actually use these bricks if I want. So right now, you can see that the bricks are leaning forward 3 degrees, and then if I pick this up until it's just about balanced, right, that's right about there, it's right balanced there. So I had 3 forward, now I'm at 30 the other way, so that's 33, an angle of 33 degrees. So in other words, I would have to raise the angle of the ramp to about 33 degrees with this configuration before the robot would tip over. And I'm only going to run the highest test at about 16 degrees, so we should be okay. So you can probably stop. Yep. Okay, so now we're going to do the test on a level 0 degree surface, and we're going to time the distance between the two white marks is 60 inches or 5 feet. So we'll go ahead and go on 3. 1, 2, 3, go. All right, so now we're going to try at this height right here, and so we have an 8 degree angle of incline, 8 degrees. And there's a stopwatch again. All right, so I'm going to go ahead and do this test now on 3. 1, 2, 3. Okay, what do you got for a time? All right, so now we have the ramp at 16 degrees. And we'll try the test now. Okay, ready? 1, 2, 3. Okay, so now we're going to do it in the high range. So that means that we need to switch the gears. And I'm gonna, again, it's important to try and get the gears to match up, so because this gear has a little hub on it, it sticks out a little further, so I'll put a little bit thicker spacer on that side. See if that works. So yeah, so that's, they're pretty much flush now. And again, now, you know, for instance, for each time this turns once, this is going to turn more than once. We have a ratio of 84 to 36. So we'll get more speed, but it will require more torque, right? Again, the force is the same. That moment arm is shorter than this one, so this axle will have more torque than this axle. And we'll see how this affects the performance on the flat and the different angles of the ramps. So you can just put this back together now, and all right. All right, so we'll just tighten this up and put the other wheel on. And again, make sure I push the axle all the way through. Okay, and then we'll do the same thing on the other side, and then we'll go ahead and do the test. Okay. All right, so now we're going to try at on level, 0 degrees in the high transmission configuration. So on 3, 1, 2, 3. What's that? So now we have the ramp set at 8 degrees, and we're in the high range, right? High speed, low torque transmission range. And so on 3, 1, 2, 3. And you can see what happened there. The motors, it required too much torque, not enough to stall it, but it started to move. But it was drawing so much current, the motor started to overheat. When the motor overheats, as you know, metals like copper, when the temperature goes up, the resistance goes up, so then we get even less torque, and then it wouldn't be able to make it up the ramp. So that was in the high-speed transmission configuration. Okay. All right. So we have the transmission set in the high-speed mode. So in other words, we'd have a lot of speed, but not that much torque. And we have the ramp right now set at 16 degrees. So if I try to go forward right now, nothing happens. In other words, the motors cannot produce enough torque with this ratio to be able to move at all. So now we're going to, yeah, so that will be good. So now we're going to put it back on the original, which is the 60 to 60, so it'll just be a 1-to-1 ratio. Okay. Whoops, I should have left those on. All right, so now we're going to put 60s back all the way around, with the 60s, they have a little bit of a hub, so we don't need to put a spacer on there on the where it goes up against the chassis. Excuse me. Okay, and then we will put a spacer on here. Again, make sure that axle is pulled all the way through. And put this other wheel back on. Make sure that axle is pushed all the way through. Right, and now again we have a 60 tooth on a 60 tooth, so it's a 1-to-1 ratio between the motor and the wheel axles. And then we'll just do the same on the other side. Is that? Okay, so this is the medium range transmission, and we're on level ramp right now, and I'm just gonna be, we have a lot of weight up the top here, so I'm just gonna be ready to catch this in case I need to. So anyways, on 3, 1, 2, 3. Now we're on an 8-degree ramp with the medium transmission. Ready on 1, 2, 3. Okay, so now we're on the 16-degree ramp. We have the transmission in the medium configuration, the 1-to-1 ratio. So we're ready to go on 1, 2, 3.
So now we have our results. We have the actual results from our lab tests, and then we can compare those to the predicted results. And so, as expected, at 0 degrees, the high ratio transmission gave us the best or the highest velocity, and at 8 degrees, as predicted, the medium transmission ratio gave us the highest velocity, and then at 16 degrees, the low transmission ratio gave us the highest velocity. And you'll notice that this seems fairly close here, but these numbers not as close. So the predicted was 36, the actual is 20. But remember that when we did the force analysis, we assumed there was no acceleration. In other words, we assumed that the velocity was constant. Since we're starting from a dead stop and the ramp isn't that long, it takes some time to get up to speed. And of course, in the high transmission ratio, just think of this, suppose you had, your bike in the highest speed, or if you have a manual transmission car, if you have that in the highest speed, and trying to slip the clutch and get up to speed, you're not going to be able to accelerate as quickly. You don't have as much extra torque as you do in the low transmission ratio. So part of the time here is that the robot has to get up to speed. Not that it necessarily would be reach exactly 36 inches per second, but it does lose some time, especially in the high transmission ratio, getting up to speed. And it's the same thing in these cases. And then down in this at the 16 degrees, they're a little bit closer, but again, remember, we're just using a hand timer here. That's not going to be exact. And notice that the velocity difference here is not that great. So, but in terms of where you want to run the motor, definitely want it to be running on this ratio. So in other words, what we see here is that these 2 points are on either side of the peak of the power curve. On this side, in the medium transmission ratio, you have high torque and lower speed. You have a ratio of 1-to-1. So again, the actual speed of the robot is fairly close. here the robot, the motor itself is running at a higher speed and a much lower torque. In terms of design, you really want to be in this kind of situation. In fact, with these VEX motors, generally I wouldn't design them for to run at more than 20% of the stall torque for any amount of time. You're just better off to have them spinning fast and use a higher ratio. And then, of course, that way you have more torque if you need it in the end. So anyways, hope this helps.